Okay, hi guys. So I hope you have tried the question which we discussed in the previous lecture. So in this lecture, we'll be continuing on seeing the solution part of the same. Okay, so let's get started. So before that, let me reiterate the question that we have been given 30 ml of a solution of KiO3 which reacted with exactly 25 ml of 0.1 m Ki in acidic medium according to this reaction. So you have to calculate the molarity of KiO3 solution, which is the first part of the question. And in the second part, you have to calculate that if 50 ml of this KiO3 solution, the molarity of which we have found in the previous part of the question, is treated with excess of Ki in acidic solution, and the liberated I2 was treated with 0.5 n of Na2S2O3. So we have to calculate the volume of Na2S2O3 which is required. Okay, so let's begin with the solution part. Okay, so millimoles of Ki would be molarity of Ki into volume which is required. Molarity of Ki which is given to be 0.1 and volume of Ki which is used was 25 ml. Hence millimoles of Ki can be calculated from this. And now if you have to calculate millimoles of KiO3, so millimoles of KiO3 would be nothing but 2.5 upon 5. And why am I writing this? Because when this reaction took place, we took point, so whatever moles of I minus is consumed in the reaction, n number of moles, if number of moles consumed here is n, then the number of moles of KiO3 consumed would be n over 5. Okay, so if millimoles of Ki consumed in the reaction would be m into V, where m is 0.1 and V is 25, so millimoles of I minus consumed in the reaction was 2.5, hence millimoles of KiO3 that would have been consumed in the reaction would be n by 5, which is 2.5 over 5, which is nothing but molarity of KiO3 multiplied by volume of KiO3, which is being given as 0.5. So now we know that 30 ml of solution of KiO3 was reacted initially. So molarity of KiO3 would be 0.5 upon 30. Okay, or we can write it as 1 upon 60. Okay, now this KiO3 was reacted with excess I minus to liberate I2, and that I2 was used with 0.15 normal Na2S2O3 solution. So we had to calculate the volume of Na2S2O3 required. So I hope you remember that in case of KiO3, milliequivalents of I2 cannot be combined or equated from first reaction with the second reaction. Hence we have to rather equate the millimoles of I2 which were consumed in the first step of the titration of the iodometric titration of Ki with KiO3 minus, and then the liberated I2 would have been used in the second step of the reaction. So total moles of the I2 that was produced in the first step would be used in the second step. We cannot equate the milliequivalents of I2 in both the cases. We have seen this case in some previous lectures. Hence I'm just writing the second part of the iteration, which is Na2S2O3 reacting with I2 forms 2 moles of NaI plus Na2S4O6. Okay, so how many millimoles of KiO3 would have been consumed when 50 ml of KiO3 was reacted with Ki? So millimoles of KiO3 consumed, millimoles of KiO3 consumed would be 1 upon 60, which is the molarity, multiplied by 50, which is the volume of KiO3 solution which is used for the titration in the first step. This is the reaction for step 2. Step 1 reaction has been given here. Okay, so step 1. So here we can see that if 5 upon 6, which is millimoles of KiO3 used would be 5 upon 6. So 5 upon 6 millimoles of KiO3 would produce how many I2? So 1 mole of IO3 would produce 3 moles of I2, and 5 upon 6 would produce 3 multiplied by 5 upon 6, which is 2.5 moles of millimoles of I2 would be produced. So millimoles of I2 produced from first step is 2.5, and this 2.5 millimoles would be used in the step 2 here. Okay, so we have to calculate the volume of Na2H2O3 which is required at the titration. So in this titration for the step 2, we can say that milli equivalent of I2 reacted would be equal to milli equivalent of Na2H2O3 reacted. Milli equivalent of I2 would be nothing but millimoles of I2 multiplied with n factor of I2 in step 2, which should be equal to millimoles of milli equivalent of Na2H2O3, which is normality of Na2H2O3 multiplied with volume of Na2H2O3. Okay, so into n factor, or is the n factor required? No, n factor is not required in this case. Why? Because this is directly normality into volume, which directly gives us milli equivalent of Na2H2O3. This volume is in milliliter. Just remember this. So millimoles of I2 were 2.5. N factor of I2 in step 2 is 2. Why? Because it is going from 0 to -1. So n factor would be 2, as there are 2 moles of I2 present in a compound of iodine. So 2.5 into 2, which should be equal to 0.15 into volume of Na2H2O3 required. So V would be 2.5 into 2 upon 0.15. That should give us 33.3 ml. Solution is required for solution of Na2H2O3 is required for titration. Next, let us see back titration. Okay, this is a new topic which we are starting, which is back titration. So back titration is this is used to find percentage purity of a sample or percentage of a substance present in a ore. Okay, so this is used to find percentage purity of sample or percentage of a sample present in percentage of a substance present in a sample. Okay, so we have impure sample of A, which means that we have substance A plus impurity. Okay, so in back titration we use 2 steps. Step 1 is impure substance A is reacted with reagent B, which is in excess. Impure substance A is reacted with reagent B, which is in excess. And step 2 is that unreacted B now reacts with another reagent C. Unreacted B reacts with another reagent C, so whose molarity and concentration or volume we already know. Okay, so we can say that total moles, or rather total millimoles, as whatever you may want to call it, total millimoles of B that has been reacted would be reacted with millimoles of A plus millimoles of C. Millimoles of B reacted with A and millimoles of B reacted with C would give us total millimoles of B that has been reacted. And milli equivalent of A present in the sample would be equal to milli equivalent of B reacted. Okay, so total rather the milli equivalents of B reacted would be total initial milli equivalents of B minus the remaining equivalent of B, and remaining equivalent of B would be nothing but the equivalent of B, or rather we should not exactly generalize it, but remaining would be coming from or derived from the equivalents which have been reacted with C, remaining equivalent of B. Okay, so in other terms, milli equivalents of A can be written as weight of A in the mixture divided by equivalent weight of A into equivalent of A into 1000. That should be equal to N1 V1 minus N2 V2. Okay, and we know that milli equivalent of unreacted B will be equivalent to milli equivalent of C, which is N2 V2. So it is coming from C. Okay, so here obviously we are not generalizing it, as I have told few seconds back. So this is under the assumption, this formula is under the assumption that n factor of B is same when reacted with A and C. Had the n factor been changed, we cannot assume this. Rather, we have to do the calculation based on number of moles then, as we did in the case of iodometric titration, in wherein we saw the reagent as KiO3. Had it been the case similar to CuSO4, where the equivalents of I2 or rather the n factor of I2 remain the same in both the steps, then we can actually equate the milli equivalent of CuSO4 with the milli equivalent of Na2H2O3 in that case. But here just extrapolating this case with the previously discussed case, so in this case also, if the n factor of B, which is common compound which has been used in both the steps, if the n factor of B is used, n factor of B in both the steps are same, then only we can compare the milli equivalents in both the steps. If not, then we cannot compare the milli equivalents. Okay, so with this we come to the end of this lecture. In the next lecture we will be seeing more concepts on back titration and possibly a question as well. Okay, so till then, good luck and goodbye.